Hello students. In the last video we had seen how to find the derivatives. Today we are going to discuss the application of derivatives. It is a very interesting and important topic and it is used extensively in physics also. So watch the video till the end. There are many fields in which derivatives are used. In general, they are used to determine the rate of change of quantities, especially in physics, to find the equation of tangents and normal, to find the turning points on the graph of a function, which we will see in this video, which will help us to locate points at which the largest or the smallest value is there, to find intervals on which a function is increasing or decreasing, and to find the approximate values of certain quantities. So what do you mean by rate of change of quantities? If a quantity y varies with another quantity x satisfying some rule, that means the function is y is equal to fx, then the derivative dy by dx, which we can write as f dash of x, is actually the rate of change of y with respect to x, and that if you find at a particular point x is equal to x0, you say it is f dash at x0. Also, we are going to use the chain rule. We have seen that the chain rule is if there are two functions, say x is a function of t, y is a function of t, then if you want to find dy by dx, then it is dy by dt upon dx by dt. Also note that dy by dx is positive if y increases as x increases, and it is negative if y decreases as x increases. First, we will discuss the concepts theoretically and then we will use in the examples which will make it clear. Now let I be an interval containing the domain of a real valued function f. Then f is said to be increasing on I if x1 less than x2 in the interval I implies that f of x1 is less than or equal to f of x2 for all x1, x2 belonging to I. Then that means in that interval, if x1 less than x2, then fx1 should be less than or equal to fx2. Similarly, decreasing means x1 less than x2 implies fx1 greater than or equal to fx2 for all x1, x2 belongs to I. You can say it is constant on I if fx is equal to c, a constant quantity, for all x belongs to I. You say it is strictly increasing on the interval I if x1 less than x2 in I implies fx1 is less than fx2. It is not equal. It cannot be equal. It is fx1 is strictly less than fx2. Similarly, strictly decreasing means x1 less than x2 implies fx1 greater than fx2. Now, a theorem says that let f be continuous on the closed interval ab and differentiable in the open interval ab. Then f is increasing in closed interval ab if f dash of x is greater than 0 for all x belongs to ab, and it is decreasing if f dash of x is less than 0 for all x belongs to ab. F is a constant function in closed interval ab if f dash of x is 0 for all x belongs to open interval ab. Now before going to the exact definitions, this is an important concept. Let us understand what do you mean by maxima and minima for a function. Now for a graph, the points where the slope becomes 0 are called stationary points. Remember, slope means your derivative. So the point at which the derivative or the tangent, we have seen in the previous video I discussed that the slope is the derivative or it is the tangent. So, for a graph, the points at which the slope becomes 0 are called stationary points. That means the tangent becomes horizontal and the derivative is 0. The points at which the function changes its path are called turning points. You can see in the graph that you are having some points which are the turning points. The points at which the function changes its path are called turning points. That means the graph was moving up, then it will go down, and if it was moving down, it will go up. So they are called turning points. Now in the given graph, you can see A, B, C are stationary points, and from that A and B are turning points also. C is not a turning point because there the graph remains the same. It neither goes from up to down or from down to up. Now maxima and minima refer to the highest and the lowest points for a function's graph in a given domain. So if we want to define a point where the function's value is higher than all other nearby points, then it is called the local maximum. The function value is higher than in its immediate neighborhood. And what is global maximum? The function value is higher than in any other point in the domain. Correct? See, these are two different concepts. We will see the difference also between them. Local means in a given neighborhood it is having the highest value, and global means in the whole interval it is having the highest value. Similarly, minimum, a point where the function's value is lower than all the nearby points, then it is called the local minimum if the function value is lower than its immediate neighborhood, and it is called the global minimum if the function value is lowest among all the points in the domain. So for maximum and minimum you have two concepts, local and global. Now let us give some definitions. We use the concept of derivatives to calculate the maximum and minimum values for various functions. Like when it is used, for example, if you want to find the maximum profit, you want to find the minimum distance, minimum cost, in those cases you need to find the maximum and minimum values for functions. Let f be a function defined on an interval I. Then f is said to have a maximum value in I if there exists a point C in I such that fc is greater than fx for all x belongs to I. The number fc is called the maximum value of f in I, and the point C is called the point of maximum value of f in I. Similarly, minimum value. F is said to have a minimum value in I if there exists a point C such that fc is less than fx for all x belongs to I, means for all the points in the interval. The number fc in this case is called minimum value, and over here the point C is called the point of minimum value. F is said to have an extreme value in I if there exists a point C in I such that fc is either a maximum value or a minimum value. The number fc in this case is called the extreme value of f in I, and the point C is called the extreme point. So extreme point covers the minimum and maximum value both. Some other definitions. A monotonic function f in an interval I is such that f is either increasing in I or decreasing in I. Correct? That means it is either increasing or decreasing. Every monotonic function assumes its maximum or minimum value at the endpoints of the domain of definition of the function. That means every continuous function on a closed interval has a maximum and a minimum value. Correct? Let f be a real valued function and let C be an interior point in the domain. Then C is called the point of local maxima if there is an h greater than 0 such that fc is greater than or equal to fx for all x in C minus h to C plus h open interval. The value of fc is called the local maximum value of f. Now see, this concept I had just explained in one of the previous slides. It is the same thing, but we are writing in the form of definition. In the neighborhood, neighborhood means in the open interval C minus h to C plus h. Correct? So same way you have the local minimum. C is called the point of local minima if there is an h greater than 0 such that fc less than or equal to fx for all x in C minus h, C plus h. That means in the given neighborhood it is minimum. So the value fc is called the local minimum value of f. You will understand it better when we see the examples. So now see, if you want to see the difference, as I discussed previously, you can have the local maxima minima or you can have the global maxima minima. What is the difference? First thing is, your global maxima minima is also called absolute maxima or minima, and the local maxima or minima is also called sometimes as the relative maxima minima. Now for the global one, it is bounded by the domain of the function, means in the whole domain it is the maximum or minimum, while for the relative it is not bounded by the domain of the function. For the absolute maxima or minima, it is the highest or lowest point of the function, while for the local maxima or minima, it is the higher or lower in the given neighborhood. So this is the main difference. Now see how to actually use it in the examples. What is the working rule? First thing is you find all the critical points, or you can say the turning points of f in the interval. That means you have to find the points x where either f dash of x is 0 or it is not differentiable. So if it is not differentiable, no question of it, but if it is differentiable, you have to find the points x at which your function's derivative is 0. Second step, take the endpoints of the interval. At all these points, calculate the values of f. Identify the maximum and minimum values of f out of the values calculated in step 3. This maximum value will be the absolute maximum value of f and the minimum value will be the absolute minimum of f. Correct? See, the points at which your derivative is 0, that means you can get the points which might be the local maxima minima. But if you want to find the absolute or the global maxima or minima, then what you need to do is you also have to find at the endpoints, and from these values, which are the maximum will give you the absolute maximum, and which are the minimum, which is the minimum, will give you the absolute minimum value of f. Now the most important thing, the first and the second derivative test, which we are going to use in most of the examples. First we will just have an understanding of it. Now if you see the given figure, before the slope becomes 0 at the stationary point, it was negative, and afterwards it gets positive. You can see from the diagram that you have the slope for the where the horizontal line is drawn, there the slope is 0. Before that you can see it is going down, means the slope was negative, and after this the slope becomes positive. So when you calculate d square y by dx square, it will be positive at the stationary point. Because when you find out the derivative, that second derivative will be positive at that point. Correct? Because it goes from negative to positive. So it means that whenever the first derivative is 0 and the second derivative becomes positive, it is the point of minima. Similarly, whenever the first derivative is 0 and the second derivative becomes negative, it is the point of maxima. Now this is how we state the first derivative test. Don't worry about this big definition. It is very easy when we actually apply it to the examples. Now the first derivative test says that let f be a function defined in an open interval I. Let f be continuous at a critical point C in I, critical or turning point. Then if f dash of x changes sign from positive to negative as x increases through C, that is if f dash of x is greater than 0 at every point sufficiently close to C and to the left of C, and f dash of x is less than 0 at every point sufficiently close to and to the right of C, then it is the point of local maxima. Similarly, if f dash of x changes sign from negative to positive as x increases to C, that means if f dash of x is less than 0 at every point sufficiently close to and left of C, and f dash of x is greater than 0 at every point sufficiently close to and to the right of C, then it is called the point of local minima. If f dash of x does not change sign as x increases to C, then C is neither a point of maxima or minima, it is called a point of inflection. It will be very clear when we discuss the examples. You also have the second derivative test. Now let f be a function defined on an interval I and C belongs to I. Let f be twice differentiable at C. Then x is equal to C is a point of local maxima if f dash of C is 0 and the second derivative f double dash of C is less than 0. The value of fc is local maximum value of f. Similarly, if x is equal to C is a point of local minima if f dash of C is 0 and f double dash of C is greater than 0. The value of f of C is called the local minimum value of f. Remember, in one of the previous slides we had just tried to understand this concept, that when for the point of local minimum the second derivative is greater than 0 and for the point of local maximum the second derivative is less than 0. The test fails if f dash of C is 0 and f double dash of C is also equal to 0. In this case, we go back to the first derivative test and find whether C is a point of local maxima, minima or point of inflection. Now see, this is actually important. In the examples, When will you use the first derivative test and when will you use the second derivative test? Both tests are for the same purpose, correct? To find the maxima and minima. But when to use which test? Now, when the first derivative test is sufficient is in the following cases. For all critical points, the first derivative test works for all critical points including those where the first derivative is 0 or undefined. When the second derivative is difficult or impossible to calculate, this is the key point. Actually, we've seen some examples that it is very difficult to find the second derivative. So, in that case, if the finding of second derivative is computationally very expensive, or you can say that means impossible, the first derivative test is useful. When the second derivative test is inconclusive, if the second derivative test yields a result of 0 at the critical point, that means double dash second derivative is also 0, then it is inconclusive. So in this case, you need to apply the first derivative test. When the second derivative test is useful, when the second derivative is easy to calculate. Remember, when it is very easy to calculate the second derivative, then this test becomes very easy. Like in some examples, to find the second derivative is a very easy thing. Then in those cases, just find out the second derivative, see whether it is less than 0, greater than 0, and you will get your answer. And secondly, to confirm results from the first derivative test. So sometimes it happens that the second derivative test can be used to confirm the conclusions which we have obtained from the first derivative test, especially when the first derivative test indicates a critical point. Also, the first derivative test is generally sufficient for finding local maxima and local minima and determining the intervals of increase or decrease of a function. The second derivative test is useful as an alternative when it's easy to calculate and when the second derivative is non-zero at a critical point. If the second derivative is 0, the second derivative test is inconclusive and we need to use the first derivative test. The first derivative test is a more general and reliable method for finding local extreme points, while the second derivative test offers a potentially faster approach when it is applicable and conclusive. So in short, first derivative test examines the sign change of the first derivative around critical points to determine local extreme points. Second derivative test examines the value of the second derivative at critical points to determine the local extrema. Local extrema means local minimum or local maximum. Okay, we start with the examples. So now the whole concept of maxima minima will become clear. A stone is dropped into a point lake and waves move in circles at a speed of 4 cm per second. At the instant when the radius of the circular wave is 10 cm, how fast is the enclosed area increasing? Now, first of all, what you have is the area of a circle. Because it is in the circular form, you know the formula of area of a circle. It is pi r square. So, rate of change means derivative. Rate of change of area with respect to time t is dA by dt. But your area is a function of radius. So, chain rule. dA by dt is dA by dr into dr by dt. So, first of all, dA by dr means the derivative of pi r square with respect to r into dr by dt. Pi r square, pi is constant, derivative of r square is 2r, so pi into 2r into dr by dt. But over here dr by dt is given to be 4 cm. See, it is given that the waves move in circles at a speed of 4 cm per second. That means dr by dt is 4 cm. So, when your r is 10, now you have to find out that at that instant when the radius of the circular wave is 10 cm, how fast is the area increasing. So when r is equal to 10, then what is the rate of change for area? Means dA by dt. dA by dt is equal to 2 pi into, from the above formula, 2 pi into r which is 10 into dr by dt which is 4, which is equal to 80 pi. That means the enclosed area is increasing at the rate of 80 pi centimeter square per second when r is equal to 10 centimeter. Remember, in all the examples, don't forget to write the unit over here. Correct? So area is increasing at the rate of 80 pi centimeter square per second. Example 2. The length x of a rectangle is decreasing at the rate of 5 cm per minute and the width y is increasing at the rate of 4 cm per minute. When x is 8 cm, y is 6 cm, find the rate of change of the perimeter and secondly of the area for the rectangle. Now two things are given over here, x and y. X is the length and y is the width of the rectangle. What else is given? First always note down what is given and what you need to find out. So you are given over here the rate of change for the length. So it is given the length is decreasing at the rate of 5 cm per minute. So remember over here it is decreasing. So we need to take minus 5 cm per minute. Don't forget this. Also the width is increasing. That means dy by dt is 4 cm per minute. So what else is given? You have to find when x is 8 and y is 6 centimeter. Perimeter formula is 2 into length plus breadth. So now derivative of perimeter with respect to time. Again over here, since over here you are having 2 into x, but what will be the derivative of x with respect to time? Dx by dt plus derivative of y dy by dt. Put the values, you will get minus 2. Hence the perimeter of the rectangle is decreasing at the rate of 2 cm per minute. Similarly area formula is x into y. So you know for multiplication of function the derivative rule is first function as it is derivative of second plus second function as it is new derivative of first function. Put the values, you will get 2 cm square per minute. That means since it is area, it is centimeter square, remember. Hence the area of the rectangle is increasing at the rate of 2 cm square per minute. Example 3. A balloon which always remains spherical on inflation is being inflated by pumping in 900 cubic centimeters of gas per second. Find the rate at which the radius of the balloon increases when the radius is 15 centimeter. Now see, over here a balloon is given and suppose r is the radius of the spherical balloon. Then what is the formula for volume of a sphere? It is 4 upon 3 pi r cube. Next what is given to us is the rate of change of volume with respect to time. That means it is given over here that a balloon which remains spherical or inflated is being inflated by pumping. What is the rate? 900 cubic centimeters of gas per second. So dV by dt is 900 cubic centimeter per second. Now dV by dt is 4 upon 3 pi, which is constant, into derivative of r cube, which is 3r square, into dr by dt. Why? Because r over here, dr by dt is the rate of change of radius. Again this is a chain rule, because when you want to find the derivative of volume with respect to time, it is derivative of volume with respect to dr into dr by dt. So this is equal to 900, which gives dr by dt is equal to 900 upon 4 pi r square. When r is 15 centimeter, dr by dt is 900 upon 900 pi, which is 1 by pi. So the rate at which the radius increases is 1 by pi centimeter per second. Next example. Sand is pouring from a pipe at the rate of 12 cubic centimeter per second. The falling sand forms a cone on the ground in such a way that the height of the cone is always 1/6 of the radius of the base. How fast is the height of the sand cone increasing when the height is 4 centimeters? See, we are doing different examples, maybe one of rectangle, sphere, cone and so on, so that you can get an idea of it. Over here you have the cone, correct? So suppose if r and h are the radius and height of the cone respectively. See, I am keeping over here r as r and h as h. You can take x and y, any variables. What is given to us? Height is r by 6, correct? 1/6 of the radius. Or you can say radius is 6 into h. Another thing which is given is dV by dt. The rate of change of volume of the cone with respect to time. It is 12 cubic centimeter per second. Volume of cone formula is 1 upon 3 pi r square h. So now you try to convert in one of the variables, correct? Either h to r or r to h. So over here we put r is equal to 6h. So volume is 12 pi h cube. By what will be the formula? dv by dt is equal to, now since our volume is a function of only the variable h, so it will be dv by dt is equal to dv by dh into dh by dt. What is dv by dh? dv by dh is 12 pi constant, derivative of h cube, it is 3h square into dh by dt. This is given to us as 12. So putting the values, we get over here that when h is equal to 4, that means when you put h as 4, dh by dt is equal to 1 upon 48 pi. Correct? dh by dt is 1 upon 3 pi h square, but when you put h as 4, in this case dh by dt is 1 upon 48 pi. So the rate at which the height increases is 1 upon 48 pi centimeter per second. Example 5. The total cost Cx in rupees associated with the production of x units of an item is given by C of x is equal to 0.007 x cube minus 0.003 x square plus 15x plus 4000. Find the marginal cost when 17 units are produced. Now see over here, cost which is given in rupees, it is a function of the number of units, where x is the number of units. You have to find the marginal. Remember, marginal cost, marginal revenue means you need to find the derivative, rate of change, correct? If you know the definition, marginal revenue or marginal cost tells you what is the rate of change of the revenue or the cost with respect to the number of units. So the marginal cost is given by dc by dx, where x is the number of units. dc by dx is just find the derivative of the given function. Derivative of x cube is 3x square, derivative of x square is 2x, and constant 15x derivative is 15, 4000 derivative of constant is 0. So now in this equation put x is equal to 17. When you put x is equal to 17, you get 20.967. Hence the marginal cost is rupees 20.967. Next example, prove that the function given by fx is equal to cos x is decreasing in 0 to pi, increasing in pi to 2 pi, and it is neither increasing nor decreasing in 0 to 2 pi. So the function fx is cos x. Now you know to find increasing, decreasing, you first need to find the first derivative. So first derivative means derivative of cos x is minus sin x. Now first case is 0 to pi. Now for each x belongs to 0 to pi, sin x is greater than 0. Remember our rule, all STC, ASTC, correct? This is the rule. In first quadrant, all are positive. Second quadrant, sign is positive. All STC, T means in the third quadrant, tan is positive. In the fourth quadrant, cos is positive. So 0 to pi means first and second quadrant. So in both the quadrants, sign will be greater than 0. So since sin is greater than 0, f dash of x is minus of sin x. It will be less than 0. We have seen a result previously that for all x, if means for all x in the given interval, if f dash of x is less than 0, then the function is decreasing. So f dash of x is less than 0, so f is decreasing in 0 to pi. Next case is pi to 2 pi. Pi to 2 pi means it is the third and the fourth quadrant. In third and the fourth quadrant, sin x is less than 0. Again all S, T, C. T and C are positive, but sin is not. So sin x is less than 0 in third and fourth quadrant. So we have f dash of x greater than 0. And so f is increasing in pi to 2 pi. F dash is less than 0. So minus of sin x. So minus minus plus. So f dash of x is greater than 0. So f is increasing in pi to 2 pi. Now if you combine both of them, obviously in some part it is decreasing, some part it is increasing. So you can say that f is neither increasing nor decreasing in whole of 0 to 2 pi. Now in the next example, fx is equal to 2x cube minus 3x square minus 36x plus 7, you have to find the intervals in which it is increasing and the intervals in which it is decreasing. The first thing is what you have to do is you have to find f dash of x and equate it to 0. Correct? So in this case you will get the critical points. So f dash of x is 6x square minus 6x minus 36, or when you simplify it and solve the quadratic equation, it gives you x minus 3 into x plus 2 equal to 0. So you are having two values of x is equal to 3 or x is equal to minus 2. These two values of x divides the whole interval in three different intervals. Means it divides R into three different intervals: minus infinity to minus 2, minus 2 to 3 and 3 to infinity. In all of these three intervals you need to check the sign of f dash of x. Let us consider the first interval, minus infinity to minus 2. It is minus infinity to minus 2, means all the values which are less than minus 2 you need to consider. So what you can do is you can, for example, put say over here minus 3. Correct? So suppose if I put minus 3, x minus 3 means minus 3 is minus 6, and if I put x as again minus 3 plus 2 it is minus 1. So it is actually negative into negative, so that will be greater than 0. So your function is increasing in this interval. Second interval is minus 2 to 3. Correct? So over here also you can take any value in between this. Suppose if I take say value as anything, say 1. So 1 minus 3 it is negative. 1 plus 2 it is positive. So it is negative into positive, which is less than 0. So your function is decreasing over here. Third case is 3 to infinity. Take any value. Say if I take x as 4. So 4 minus 3 is plus. 4 plus 2 is again plus. Plus into plus greater than 0. So the function is increasing. So now what we can say that f is increasing. In fact it is strictly increasing. Correct? It is not equal to, because it is over here you are having the open interval. So f is increasing in the intervals minus infinity to minus 2 and 3 to infinity, while the function is strictly decreasing in the interval minus 2 to 3. However, function is neither increasing nor decreasing R, because when you consider the whole of R, at some places it is increasing, some places it is decreasing. So you can say f is neither increasing nor decreasing in R. Example 7. Prove that the function f given by fx is equal to log of mod of cos x is decreasing on 0 to pi by 2 and increasing on 3 pi by 2 to 2 pi. So first thing is again over here find f dash of x. F dash of x, derivative of log is 1 upon, suppose you have log x, derivative is 1 upon x, log of mod of cos x. It is first of all 1 upon cos x into derivative of cos x, which is minus sin x. So in general you can say it is minus tan x. Now over here 0 to pi by 2. 0 to pi by 2 means it is the first quadrant. First quadrant means over here tan, in the first quadrant 0 to pi by 2 tan is increasing. Why? Again all as ASTC or all STC, first quadrant everything is greater than 0. So minus of tan x means minus of tan x means minus into plus, which is less than 0. So that is decreasing. In 3 pi by 2 to 2 pi means it is the fourth quadrant. In the fourth quadrant ASTC, only over here cos is positive, so tan is negative. So over here minus of tan, so negative into negative is greater than 0. So it is increasing. Correct? Next one. For what values of a the function f given by fx is equal to x square plus ax plus 1 is increasing on close interval 1 to 2. First thing, find the derivative. So f dash of x is equal to 2x plus a. Now over here it is already given that in the interval 1 to 2 fx is increasing, means your f dash of x is greater than 0. That means 2x plus a is greater than 0. 2x plus a is greater than 0 means 2x is greater than minus a, or you can say a is greater than minus 2x in the close interval 1 to 2. So now over here take the extreme points. So over here when you put x is equal to 1, it shows that a greater than minus 2, and if x is equal to 2, a greater than minus 4. So when you combine both of them, if your a is greater than minus 2, a greater than minus 4, that means first of all, if a is greater than minus 2, obviously it will be greater than minus 4. So the least or the minimum value for a is minus 2. Example 9. Find the maximum and minimum values if any of the following functions. First function is fx is equal to mod of x plus 1 minus 1. Now we know that mod function always has value greater than or equal to 0. So mod of x plus 2 is always greater than or equal to 0. When mod of x plus 2 is greater than or equal to 0, fx means mod of x plus 2 minus 1 is greater than or equal to minus 1 for all x. That means the minimum value of fx is minus 1. Now, when the value of fx is minus 1, obviously x plus 2, mod of x plus 2 is 0. That means x is minus 2. So over here, the minimum value exists. Minimum value of fx is minus 1, but the maximum value can go anything up to infinity. So the maximum value of fx tends to infinity. So actually, there is no one such maximum value which exists. Second function is hx is equal to sine 2x plus 5. Now we know that sine function, what is the range? Minus 1 to 1. So sine 2x is between minus 1 to 1. That means minus 1 plus 5 less than or equal to sine 2x plus 5 less than or equal to 1 plus 5. So sine 2x lies between 4 and 6. So here the minimum value of the function is 4 and the maximum value is 6. Next example. Find all the points of local maxima and local minima for the given functions. First function is fx is equal to x cube minus 6x squared plus 9x plus 15. So first thing is you find f dash of x and equate to 0. When you find f dash of x, solve the quadratic equation, you get x minus 3 into x minus 1 equal to 0, which gives x is equal to 3 or x is equal to 1, which are the critical points. And from that we have to check which are the points of local maxima or minima. So first of all, let us consider 3. We are going to use the first derivative test, so pay attention how to use it. First point is x is equal to 3. Now you take the values which are near to 3 from the left side and from the right side. That means from the left side means a value which is near to 3, little bit less than 3. So say if you take for example 2.9 and you put in f dash of x. So what will you get? 2.9 minus 3 into 2.9 minus 1. Correct? So it is negative into positive. So it is less than 0. When your x approaches 3 from the right side, means little bit more than 3, 3.1 say. So 3.1 minus 3 into 3.1 minus 1. Both are positive, so plus into plus greater than 0. Second point is 1. When it approaches to 1 from the left side, say 0.9, 0.9 minus 3, 0.9 minus 1. So negative into negative is positive. From the right, say 1.1, 1.1 minus 3 into 1.1 minus 1. So it is negative into positive, which is less than 0. So now by the first derivative test, x is equal to 3 is a point of local minima. Why? Because from less than 0, it changes to greater than 0. Correct? I have explained this in one of the slides previously. When it goes to positive, from negative to positive, it is the point of local minima. And when it goes from positive to negative, it is the point of local maxima. So x is equal to 1 is the point of local maxima. And when you put x is equal to 1 in your function fx, the maximum value of function means f of 1 is 19. So by the first derivative test, x is equal to 3 is a point of local minima with the local minimum value of function f of 3 is equal to 15, and x is equal to 1 is a point of local maxima with local maximum value f of 1 is equal to 19. The second example, fx is equal to sin x minus cos x, and x is between 0 to 2 pi. Correct? So what is the derivative? F dash of x will be, derivative of sin is cos, cos is minus sin, so f dash of x is cos x plus sin x. When we equate it to 0, you get sin x is equal to minus cos x, or sin x by cos x means tan x is equal to minus 1. When is tan minus 1? Tan is minus 1 when in 0 to pi consider. Okay, so in 0 to pi tan is minus 1 when x is 3 pi by 4 and x is 7 pi by 4. Correct? So you have two values. As in the second and fourth quadrant, tan is negative. Now see, in the second quadrant, all A, S, T, C. So in the second quadrant, tan is negative. Even in the fourth quadrant, tan is negative. So your f dash of x, now let us check its sign for x is equal to 3 pi by 4 and 7 pi by 4. Correct? At 3 pi by 4, f dash. Now see, over here we are using the second derivative test. In the previous example we had used the first derivative test, but here finding the second derivative is easy. So we will use the second derivative test. First derivative is cos x plus sin x. When you again differentiate it, you will get minus sin x plus cos x. At both the points, let us check the sign for second derivative. At x is equal to 3 pi by 4, f double dash of x is minus sine 3 pi by 4. 3 pi by 4 can be written as pi minus pi by 4. We have seen this simplification in trigonometric functions, but once again. Now, sine of pi minus pi by 4. Correct? Pi minus pi by 4 means it is in the second quadrant. In the second quadrant, sine is positive. So, sine pi by 4, you know that is 1 upon root 2. But outside there is a minus sign. So, it is minus 1 upon root 2. For cos, in the second quadrant, cos is negative. So, cos pi by 4 is 1 upon root 2, but you will get a minus sign. So, it is minus 1 upon root 2, minus 1 upon root 2. So, that is minus root 2, which is less than 0. So, at x is equal to 3 pi by 4, you are having over here fx is equal to, at the same moment we are also finding, we are putting this value of x in our original function fx and just finding the value of the function. So when you put x is equal to 3 pi by 4 in original function fx is equal to sin x minus cos x, what do you get? Sin 3 pi by 4 minus cos 3 pi by 4, which is root 3. Now at 7 pi by 4, again 7 pi by 4, you can write it as 2 pi minus pi by 4. So 2 pi minus pi by 4 means fourth quadrant. Fourth quadrant sign is negative. So, and outside also negative sign is there. So negative into negative will turn positive. So it will be 1 upon root 2. For cos of 2 pi minus pi by 4, cos is positive in the fourth quadrant. So it is 1 upon root 2. So it is 1 upon root 2 plus 1 upon root 2, which is 2 upon root 2 or root 2, which is greater than 0. Again at x is equal to 7 pi by 4, the value of our function fx is minus root 2. So now since f double dash of x is less than 0 for x is equal to 3 pi by 4, x is equal to 3 pi by 4 is a point of local maxima, and x is equal to 7 pi by 4 is a point of local minima because the second derivative is greater than 0. Correct? And we have also found the value of the function at the given points. So if you want to just remember it, it is sort of like just the opposite. For the local maxima, what do you need? The second derivative should be less than 0. And for the local minima, what you need is the second derivative should be greater than 0. Example next. Find two positive numbers x and y such that their sum is 35 and the product x square y raised to 5 is maximum. Right? So now first of all what is given to us is two numbers x and y. X plus y is 35. Remember both are positive. And another thing which is given is product x square into y raised to 5. This should be maximum. So first of all x plus y is 35 means y you just convert always for all these type of examples, just convert it into one variable. Correct? So let y will be equal to 35 minus x. Now you find the first derivative f dash of y. F dash of y means first of all your fx is your what should be maximum, which function? X square into y raised to 5. So that I have simplified and written x square into 35 minus x whole raised to 5. First derivative, it is multiplication of two function. First of all, keep one function as it is, take the derivative of second function plus second function as it is into derivative of first function. You know this rule for multiplication of function, how to find the derivative. So when you simplify it, you get the first derivative as x into 35 minus x whole raised to 4 into 70 minus 7x. Take care for the simplification. Now when you equate this to 0, you get three values of x. First is x equal to 0. Second is x will be x minus 35 is 0 means x is 35. And 70 is equal to 7x means x is 10. Correct? But x is equal to 0 and x is equal to 35. If you put x as 0, y will be 35, and if you put x as 35, y will be 0. That is not possible because both are positive. So only possible values is x is equal to 10. Now we need this function to be maximum. So let us check whether it satisfies the condition for being the maximum. Here we use the first derivative test, because again to find the second derivative in this case is little bit complicated, and first derivative will easily give the answer. So we check the values for f dash, means the sign of f dash for values of x which are close to 10 from the left and from the right. First of all, say from the left, if I take x as say 9.9 and put in the given function, correct, f dash of y, when I put that value in that, if I put as 9.9, what will it be? X 9.9 is positive. 35 minus 9.9 whole raised to 4, that is also positive. 9.9 into 70, that is less than 70, so that term is also positive. So plus plus plus, it is greater than 0. Now suppose if your value of x is close to 10 from the right, means little bit more than 10, 10.1 say. So 10.1, 35 minus 10.1 raised to 4 is positive. But 10.1, when I put in 70 minus 7x, it will be less than 0. So the whole f dash of x sign will be less than 0. Sorry, f dash of x sign will be less than 0. So now by the first derivative test, the local maxima lies at x is equal to 10. What is the condition of maxima? When you go from left to right over here, it goes from greater to less than 0. So it is the point of local maxima. So the local maxima lies at x is equal to 10, and hence the required numbers are 10 and 35 minus 10, which is 25. Correct? Now also remember, the same example could also be done by taking x is equal to 35 minus y. Same thing, here you will be getting the same answer, and that is the first condition. You will be getting the same answer if you take x is equal to 35 minus y. And also, instead of using the first derivative test, if you had used the second derivative test, you could again get that this is the point of local maxima. But since it is tedious, in this example we are using the first derivative test. Next example, a rectangular sheet of tin 45 centimeters by 24 centimeters to be made into a box without top by cutting off square from each corner and folding up the flaps. What should be the side of the square to be cut off so that the volume of the box is maximum? Now see, first of all, rectangular sheet, length 45, breadth 24, correct? Height, what will be that height? Now from this we need to actually make a box type of structure by cutting off square from each corner and folding the flaps. Correct? So let height, that means the side of square to be cut, that height let it be x centimeter. Just imagine the diagram. So now volume, it is length into breadth into height. Volume for a cuboid will be length into breadth into height. So for this box which you are making, what will be the length? 45 minus 2x, because from both the corners you are cutting off xx, correct, that height. So it will be 45 minus 2x, and same way breadth will be 24 minus 2x, because again from both the corners you are cutting xx, so 24 minus 2x into the height which we have assumed to be x centimeter. So we have to actually find this value of x so that the volume of the box is maximum. Okay, so first take the first derivative, so dv by dx, v is a function of x, dv by dx, when you use the multiplication rule and simplify the whole equation, you will get a quadratic equation 12x square minus 276x plus 1080. Okay, f dash of x, when you equate it to 0, what you will be, and solve the whole quadratic equation. Take care while solving the quadratic equation, you will get x minus 5 into x minus 18 equal to 0. So which gives x as 5 or 18. But if you put 18, Then the breadth would be 24 minus 36, which is minus 12, which is obviously length and breadth cannot be negative. So it is not possible. So x is equal to 5 is our turning point. So from the first equation, when you put x is equal to 5, and here we are using the second derivative test. So we have the first derivative. From that, when you find the second derivative, first derivative equation is 12x square minus 276x plus 1080. Find the second derivative will be 24x minus 276. In that you put our point 5, you get it less than 0. That means x is equal to 5 is a point of maxima, and x is equal to 5 will give us the maximum volume. Therefore, a square of side 5 cm should be cut to get the box with maximum volume. See, we are doing different types of examples so that you get a clear idea of this portion maxima and minima, which is really very important. Prove that the volume of the largest cone that can be inscribed in a sphere of radius r is 8 by 27 of the volume of the sphere. So first of all, what is given? First two things you need to know: the formula for volume of sphere 4 upon 3 pi r cube, volume of cone 1 upon 3 pi r square h. What do we want to maximize? You want to maximize the volume of the cone. So you have seen the formula, you have 1 upon 3 pi r square h, and what is given to us is sphere. Let the radius of the sphere be capital R. It can be seen from the diagram, correct? So this capital R, you need to convert it to, we need to convert our small r in terms of capital R. Okay, then only we can maximize the function. So you can see the diagram over here, that capital R is the radius of the sphere, small r is the radius of the cone. Now over here we know that h is the height of the cone, so we can say that h minus r, this portion you can see from the diagram, by Pythagoras theorem we can say capital R square is equal to small r square plus h minus r whole square. When you simplify this, you get the equation r square plus h square minus 2h are equal to 0, or r small r square is equal to minus h square plus 2hr. See, I am keeping it in the terms of r and h only so that it is very clear to you, the formula. Now volume of cone 1 upon 3 pi r square h, in that for small r you put the, for small r square you put the equation we have just obtained, minus h square plus 2h capital R. So first equation, volume is equal to 1 upon 3 pi into 2h square capital R minus h cube. Now we find the first derivative and equate it to 0. So it is 1 upon 3 pi is constant. Remember over here capital R is constant. Why? Because it is given to us, correct? Already the sphere is given to us, so capital R is constant. So it will be 2r constant to derivative of h square, which is 2h. So it is 4hr minus 3h square. When you equate it to 0, you get 4 capital R is equal to 3h. So h is equal to 4 by 3r. So this is our turning point. Now we need to find the second derivative to check our condition for maxima, because we want the largest cone, correct? So what will be the second derivative? Second derivative, from the first equation you find the second derivative. It is 1 upon 3 pi, again 2r over here, 1 upon 3 pi, 4r is constant into derivative of h, which is 1, derivative of 3h square is 6h. In the second derivative equation, when you put our turning point value, means 4 upon 3r, and you put it in the equation of v double dash, what do you get? Pi upon 3 into minus 4r, and obviously this is less than 0 because it has a negative sign. So it gives us the point of maxima. So now in our example we have got the turning point. We know that the volume of the cone 1 upon 3 pi r square h, in that when you put 1 upon 3 pi into our r square in terms of capital R, so it is minus h square plus 2hr into h. Already we have this formula, but we have found our turning point for which the volume is maximum. So that is h is equal to 4 upon 3 r. put over here h is equal to 4 upon 3 r, and you just simplify the equation. Again I am telling you, take care by simplifying the equation. You will get 16 pi capital R square by 27 into 2r by 3. So actually it is 8 upon 27 into 4 upon 3 pi r cube. But what is 4 upon 3 pi r cube? It is the volume of sphere. So it is 8 upon 27 volume of the sphere. Next example. Show that the semi-vertical angle of right circular cone of given surface area and maximum volume is sine inverse 1 upon 3. So first of all, what is the formula for surface area of cone? It is S is equal to pi r into r plus L. What is the volume of the cone? 1 upon 3 pi r square h. Now suppose if L is the slant height, you know that for a cone h is the height, r is the radius and L is the slant height, and you know that L square will be equal to h square plus r square. How do you define semi-vertical angle? Semi-vertical angle, say theta, is the angle between h and L. It is called the semi-vertical angle. So now you want to show that the semi-vertical angle, that theta of a right circular cone of given surface area is given, and maximum volume, that angle is sine inverse 1 upon 3. So first of all, S is given to us, and so suppose just take your k as S upon pi. So what will you get? R into r plus L. Actually why we are doing this is because S is given to us, so it is a constant for us, pi is constant. So S upon pi is, say, some another constant, say k, which is equal to r into r plus L. So r square plus r into L, or we can say k minus r square is equal to r into L. Square both the sides. When you square both the sides, simplify the equation, put L square as h square plus r square. So from that you can get the value over here of r square in terms of k. K is a constant in terms of basically h. So r square is equal to k square upon h square plus 2k. Now why we are doing this is, again I am telling you, because we need to convert it into one variable so that it can be simplified and we can find the derivative. Now our volume of cone is 1 upon 3 pi r square h. Pi by 3 into small r square, the value which we have just found out, k square upon h square plus 2k into h. So now we can see our function volume is a function of just one variable, which is, say, h. Okay. So now we find the first derivative, dv by dh. Take care, use the quotient rule. You know the quotient rule. Use the quotient rule for derivatives and simplify and find the first derivative. Equate it to 0. So now when you equate this term to 0, denominator will go. So only you will be remaining with 2k minus h square is equal to 0, or h square is equal to 2k, which gives h is equal to plus or minus root of 2k. But we know height cannot be negative, so h is equal to root of 2k. This is the turning point which we have found. Next step. Now we have found h is equal to root of 2k. Now here, see, finding the second derivative would be tedious. You can see that from the first derivative equation. So we use the first derivative test. Correct? So near the turning point, we try to evaluate the value. So close to root of 2k from the left, say h is less than root of 2k. That means your h square is less than 2k. Now when your h square is less than 2k, just the equation for v dash is given. In that, if you put h square less than 2k, then you know that the numerator 2k minus h square will be greater than 0. Correct? And suppose if your h is greater than root of 2k, means h square is greater than 2k, then the numerator 2k minus h square, that term will be less than 0. Correct? All other terms are positive, so no problem. So but that term will be less than 0. So what will be the sign of v dash? The sign of v dash, when you go from left to right, it will be greater than 0 to less than 0. So we have obtained that as the point of maxima. Hence the maximum volume is obtained at h is equal to root of 2k. Now we have to find our semi-vertical angle. So we put h is equal to root of 2k. in r square is equal to k square upon h square plus 2k. So when you simplify it, you get r is equal to root k by 2. That means r square is k by 4. So now we have r square k by 4 and h is equal to root of 2k. You put it in the equation L square is equal to h square plus r square. So you get L square as 9k by 4 or L is equal to 3 root k by 2. Now just see the diagram over here. You want theta, correct? Sin theta. What is sin theta? Sin theta is opposite side upon hypotenuse. So opposite side will be r and hypotenuse is L. So r upon L, correct? R is root k by 2 and L is 3 root k by 2. So sin theta will be 1 upon 3. So theta will be sine inverse of 1 upon 3. Find the shortest distance of the point 0c from the parabola y is equal to x square where c is between half and 5. First of all, the equation of parabola is y is equal to x square. So let hk be any point on the parabola. So we can find the distance of that point from our point 0c. Let d be that distance. You know the distance formula. Distance is equal to square root of difference of x coordinate square plus y coordinate square. So d is equal to root of h minus 0 square plus k minus c whole square. Now our point hk lies on the parabola. So it satisfies the equation y is equal to x square. Y coordinate is k, x coordinate is h. So k is equal to h square. Again, why we are doing this is we want to convert it into one variable. So in the formula of d, just put k is equal to h square and simplify. So you get and square both the side. By squaring both the side, you can just simplify the equation. D square is equal to h square plus h raised to 4 plus c square minus 2h square c. Now for taking the derivative, see you can either find the derivative directly of d, which is root of a quantity. So root x derivative is 1 upon 2 root x. Or what you can do is d square derivative is 2d into d dash. And right hand side it will be 2h plus 4h cube minus 4ch. Any of the ways you do, you can get the answer. So what do you get? D dash of h is equal to 2h plus 4h cube minus 4ch upon 2d. When you equate it to 0, you get 2h plus 4h cube minus 4ch is equal to 0. Or when you simplify it, you get over here 2h square is equal to 2c minus 1 or h square is equal to 2c minus 1 by 2. So what we have obtained is h square is equal to 2c minus 1 by 2. Now we have got our turning point. H square is equal to 2c minus 1 by 2. So we use the first derivative test. Now you take the value over here which is near to this point from the left hand side and from the right hand side. From the left hand side means your h square is less than 2c minus 1 by 2. In the formula of d dash, if your h square is less than 2c minus 1 by 2, what happens is h square less than 2c minus 1 means your numerator in d dash that will be less than 0. And suppose if you are approaching from the right, means h square is greater than 2c minus 1 by 2, then 2h square greater than 2c minus 1. So the numerator in the d dash formula that will be greater than 0. So what happens is when you go from left to right, it becomes positive. That means it is the point of minima. So by the first derivative test, dk is minimum at h square is equal to 2c minus 1 by 2. Okay. Now you put the value, you put this value in the equation of d to get the minimum distance. So in that, when you put over here h square is equal to 2c minus 1 by 2 and obviously your k is equal to h square, you simplify the equation, you get d is equal to root of 4c minus 1 by 2, which is the required distance. Now remember over here in this example, we have used the first derivative test as the second derivative test. To find the second derivative would be difficult. And secondly, one more thing, also we can find the value of k instead of h square. That means you can have your function of derivative in the variable k also. Here I have taken the variable h, you could convert it into variable k also, correct? But the answer for D obviously would remain the same. A cylindrical tank of radius 10 meter is being filled with wheat at the rate of 314 cubic meter per hour. Then at what rate the depth of the wheat is increasing? So what is given to us is the volume. You know that the volume of the cylinder is given by pi r square h, and here r is equal to 10 is given. Also the rate at which the wheat is being filled is given, that means dV by dt 314 cubic meter per hour is given. What we need to find is the rate at which the depth of the wheat is increasing, means depth means height, so we need to find dH by dt. By the chain rule, dV by dt is equal to dV by dH into dH by dt. Now put R is equal to 10 in the formula for V, so it is V is equal to 100 pi H. Find dV by dt. dV by dt is 100 pi into dH by dt, correct? And this is given to us as 314. So make dH by dt as subject of formula, you get 1. So the depth of the wheat is increasing at the rate of 1 meter per hour. Find the intervals in which the given function f is firstly increasing and second decreasing, correct? So now our equation of f is fx is equal to 4 sin x minus 2x minus x cos x upon 2 plus cos x. So first thing is you just simplify this function. So it is 4 sin x upon 2 plus cos x minus x. Find the derivative. Take care while finding the derivative. We are applying the quotient rule to find the derivative. So after simplification, when you find the derivative, you will be getting it as cos x into 4 minus cos x upon 2 plus cos x whole square. Now we have found f dash of x. First case is we want to find where it is increasing. So by definition fx is increasing if f dash of x is greater than or equal to 0. Now in f dash of x, if you see, cos x ranges minus 1 to 1. So 4 minus cos x obviously will always be greater than 0. In the denominator also 2 plus cos x whole square, that will also be greater than 0. So it just depends on cos x. And for cos x, you know that in the first and fourth quadrants cos x is greater than or equal to 0. So f dash of x will be greater than or equal to 0 in the first and fourth quadrants. So fx is increasing when x is between 0 and pi by 2 and when x is between 3 pi by 2 and 2 pi. Second case is fx is decreasing if f dash of x is less than or equal to 0. So again in f dash of x, cos x is less than or equal to 0 in the second and third quadrant. So fx will be decreasing in the second and third quadrant, means between pi by 2 and 3 pi by 2. Example 18. A tank with rectangular base and rectangular sides open at the top is to be constructed so that its depth is 2 meter and volume is 8 meter cube. If building of tank costs rupees 70 per square meter for the base and rupees 45 per square meter for the sides, what is the cost of the least expensive tank? First of all, rectangular base, rectangular sides. So volume of a cuboid formula, we know it is L into B into H. It is given over here, H is 2 and volume is 8, correct? So 8 is equal to 2 into L into B, that means L into B is 4, or we can say B is equal to 4 upon L. Remember, again we try to convert it into one variable. Now for the cost of the base, it is given 70 per meter square. So cost of the base will be rupees 70 into L into B. Why? Because base is rectangular. Base is rectangular, so the area of the base is length into breadth into the cost per meter square. So 70. So 70 L into B. Now cost for the four sides. This is like, imagine you are in a room. It is of this kind. So cost for the sides is rupees 45 per meter square. Now there are four sides, and you know that for the four sides you have 2 into B into H plus 2 into L into H, correct? This will be giving you the area for the four sides into 45. So 45 into 4B plus 4L. which is equal to rupees 180L plus 180B. Now total cost will be cost for the base and cost for the 4 walls. So it is 70LB plus 180L plus 180B. Now you can write B as 4 upon L. So you will get the whole formula in the terms of L. Find the first derivative dc upon dl and equate it to 0. So when you equate it to 0, you get over here L square is equal to 4. That means L is equal to plus or minus 2, but you know length is always positive, so L is equal to 2. Now we use the second derivative test to find the second derivative. Second derivative is minus 720 into minus 2L raised to minus 3. That means 720 to 2 upon L cube. Now we know that this would always be greater than 0. Correct? So the cost is minimum. Since second derivative greater than 0, the cost is minimum at this point L is equal to 2. Now minimum cost is achieved at L is equal to 2. Put L is equal to 2 in our formula of cost which we had obtained. You will be getting the total cost as rupees 1000. Next example, show that the height of the cylinder of maximum volume that can be inscribed in a sphere of radius r is 2r by root 3. Also find the maximum volume. It is given to us, we know that volume of a cylinder is pi r square h and the radius of the sphere is say capital R. Just see the diagram. Suppose the radius of the sphere is capital R and that for the cylinder is small r. So we can see from the diagram capital R square will be equal to h by 2 whole square plus small r square. So small r square is equal to capital R square minus h square by 4. So volume is pi into r square minus h square by 4 into h. Just simplify this equation. Now find the derivative of v with respect to h. So dv by dh is equal to 0 will give you pi r square is equal to 3 upon 4 h, that means is equal to 3 upon 4 pi h square. So small h square is equal to 4 upon 3 r square. So h is equal to 2 by root 3 r. Why? Because it is always positive. So obviously we don't consider the negative value. H is equal to 2 upon root 3 r. Now h is equal to 2 upon root 3 r. We use the second derivative test. The second derivative is minus 3 upon 4 pi into 2h. So obviously at h is equal to 2 upon root 3 r, it is less than 0. Correct? Because h is positive, minus 3 by 2 pi into h, so it is less than 0. So we get the maximum value at h is equal to 2 upon root 3 r. Find the maximum volume, put the value of h as 2 upon root 3 r in v and simplify it. You get the maximum volume as 4 pi r cube upon 3 root 3. Derivative can also be applied to find the slope and normal to the curve. We are not going to discuss it in detail in this video, but we'll just take an example to understand it. Basically, the slope of the normal to the curve at a given point is the negative reciprocal of the slope of the tangent line to the same point. That means if you see the diagram, you have the tangent, correct? How do you get the tangent? By the slope, that means the derivative. Now, suppose that tangent is m. Then to find the slope for the normal, normal means the line which is perpendicular. So to find the slope of the normal, we first find the derivative of the curve's equation. So that will give you the slope of the tangent. Then you take the negative reciprocal of the tangent slope to find the normal slope. That means, for example, if you are having the curve y is equal to 2x square plus 3 sin x, then if you want to find the slope of the tangent and normal to this curve at x is equal to 0, first of all you have your equation, find the derivative. So it is 4x plus 3 cos x. At x is equal to 0, this derivative, what is derivative? Basically the tangent. Suppose that is m. Slope of the tangent is m. You put x is equal to 0, so 4 into 0 plus 3 into cos 0. Cos 0 is 1, so this is 3. To find the slope of the normal, just take the reciprocal, negative reciprocal of m. That means minus 1 by m. So it is minus 1 by 3. In this video, we have seen the concept of maxima, minima, and all the examples are explained thoroughly. So please do like and share the video and subscribe to the channel for other math videos.